Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, time to get started. Thanks everyone for joining the lab tutorial this afternoon. We have a very, very special speaker today. I don't know if there's anyone in the room who doesn't know Andrew Herbert, but I'll quickly introduce his past life to you. So Andrew received his Bachelor of Science from Leeds University in 1975 and a PhD from Cambridge in 1978. And the topic was a microprogrammed operating system kernel. Nice generic title. He then joined the computer lab as an assistant lecturer. In 1985, I'm jumping over a lot of years here now. He
finally submitted? Oh, no.
He founded a company, APM, which was driving a project called ANSA, the Advanced Network System Architecture. And in 1996, he founded another company, Digitivity. And then Citrix bought both those companies a couple of years later. And Andrew became the director of advanced technology there. And then in 2001, we were lucky enough for Andrew to join Microsoft Research here as an assistant director, and he became a managing director in 2003 and retired in 2011. So obviously he hasn't fully retired because he is now onto another project, which is recreating the famous EDSAC computer. Over to you, Andrew.
Thank you, Torren. It's a great pleasure to be here in the building that I helped raise the money for but ran away from doing the design of, so you can't blame me for the internals if you don't like them. So what I want to do is tell you about the EDSAC Replica Project. This is a computer built at Cambridge University that the project started in 1947. It ran its first program on the 6th of May, 1949. So that's rather older than me. I noticed Tony is in the room, so he can probably help me cover some of the history of that period, because I know he was also active in the computer industry from the earliest days. So our plan is to build a working reconstruction of EDSAC, the University of Cambridge's first computer, as it was on the day when it ran its first program. We're being quite particular about the date because the machine actually lasted for about 10 years. And given that computing was being invented at that time, they changed it almost month by month, and the machine at the end of its life was significantly different to the machine at the beginning. And from our point of view, the historical significance is really the day in which it started running its first programs properly, and on which some of the early work was done. So why would you want to do that? There are a number of reasons. The project is sponsored by the Computer Conservation Society, which is part of the British Computer Society, and the National Museum of Computing, which is at Bletchley Park. And certainly the mission of the Bletchley Park Museum is to celebrate British computer technology, and the UK was very active in the early days in computer hardware. Indeed, was in a leadership position throughout the 1950s, certainly. Something you wouldn't know if you look at modern computing. And the Computer Conservation Society essentially shares that aim more broadly. Importantly, we'd like to understand how EDSAC was built and how it worked. The early pioneers were so keen to get on to the next systems that when EDSAC was finished with, they were well into the design of its replacement, which was magically called EDSAC 2. There was actually an EDSAC 1.5, and you can ask me about that in the reception afterwards. They just scrapped the machine. And as far as we know, EDSAC is at the bottom of Milton Road tip because they opened that tip at that point, and that's where everything went. Very few pieces were kept. There are a few things in a couple of museums, but very, very little. When Maurice Wilkes, who was the man who designed the machine, was asked about its history, he asserted everything you needed was in the university library. It didn't quite work out like that. And so as a project, we're essentially having to reinvent EDSAC from photographs, from partial documentation, from memories of people who were involved in the machine. None of the pioneers who actually designed and built it have survived, but some of the users are still with us, and that helps. And in doing that, you need to tap into expertise in designing computers using these things called thermonic valves. They're what predated transistors. You can have a look at these. Catch! You're all sitting around the back of the room. Mitch? There you go. You could pass those around. Those are EF55s. They're absolutely dead common. These I won't quite throw around, but the dates on the boxes are quite interesting. They'll survive that experience. They're remarkably tough, actually. But knowing how to design circuits using those kind of components is a forgotten art, and so we're having to learn that. And the aim is to have the machine as an educational resource at the National Museum of Computing in Bletchley Park. And I would certainly commend to all of you a trip across to Bletchley Park. Indeed, I commend 2 trips, because the Bletchley Park Museum, with all the stuff about the code breaking, Enigma machines and so forth, is quite interesting. And you could easily spend a day just doing that. And then the National Museum of Computing is on the same site, actually in the world's first purpose-built computer room, H Block. It was built for the Colossus code-breaking machines. And they have now quite a large collection of working computers. And the ethos, National Museum of Computing, is British stuff in the main, and keep it working or make it work if it wasn't working. And indeed, while looking after EDSAC, it seems I've picked up 2 or 3 other computers that I have to look after now as well, because I use them as a student. So I'm also fixing various transistor machines. So why is EDSAC important? Why should we build a replica of EDSAC rather than some other machine? Our claim is that it's the first practical, general-purpose, electronic stored program computer. The fact I've strung so many adjectives together is a hint that lots of people claim to have the first ... computer. And indeed, a lot was going on in the late 1930s, early 1940s, where it's actually impossible to kind of put your finger on one thing and say that was precisely the first. The key point about EDSAC was it was the first machine that was built to be a computer to provide a service to an organization. It was built in what was called the Mathematical Laboratory of the University of Cambridge. That was an organization set up just before the Second World War to contain, at the outset, mechanical calculating machines to help scientists, engineers, mathematicians in the university use those machines to do their sums. If you go back to the period before we had computers in the early 1940s, you either had to do your mathematics on paper, and you were very reliant on books of tables, or you use various kinds of mechanical hand calculators, and there were various larger scale machines that could be used to solve certain kinds of equations. You essentially built mechanical analog models of things. That was your only way of doing large scale computation. So the university had a mathematical laboratory to house those things. Wilkes, who designed and built the EDSAC, was hired as a demonstrator before the war. When he came back after his war service, he became the director, and he decided Cambridge needed a computer that people could use to do their sums. So it was the first machine that was built, not as an experiment in electronics, that could be used by others. In its time, it was the biggest leap in computing power that a user community ever had. We're used to Moore's law, and our computers double in power every 18 months, or certainly we've had that until fairly recently. If you look at the speed that EDSAC could do calculations compared to the previous set of hand-driven machines in the mathematical laboratory, it was 1,500 times faster, which is just a startling increase in what could be done. And indeed, it led to 3 Nobel Prizes in fairly quick succession, because it let people work on larger amounts of data and do more complex calculations than were possible by hand. The other aspect of EDSAC, which, given I'm inside Microsoft, is important to bring up, is actually it was the first machine on which serious thought was given to software. How people program it, how you organize programs, how you make it easier for people to write correct and well-formed programs. In fact, in EDSAC, you didn't actually have to know the binary machine code, which is quite unusual. You could fit your programs are read in. They were in a symbolic textual notation, very simple. On most other machines of that period, you had to patch up wires or put your programs in by waggling hand keys up and down, right at the level of the machine itself. And very quickly, an extensive library of subroutines provided that did all the typical mathematical calculations that people needed. And so the early users could solve their problems by gluing together a set of these subroutines, a little bit of code that passed the data through in the right sequence, and get the answers they want.
So should we understand that saying it kind of had a built-in assembler?
Exactly.
That's what these symbolic programs
Yeah,
do.
I'll tell you a bit about programming. Hold on. It's not functional, unfortunately, but I can give you symbolic addressing, which for the period was quite impressive. So as I said, it contributed to a number of advances. Paul Kendrew and Max Perutz used it for analyzing X-ray crystallography data and reducing that data down to work out the structure of molecules. That's essentially a classic data reduction task. We have just found in the Bodleian Library in Kendrew's papers all his EDSAC programs. What we haven't found is the data. But we've got the programs. We may be able to synthesize the data by talking to a modern X-ray crystallographer and say, if you're analyzing it this way, what did the original data look like? Be a big project. Martin Ryle, the astronomer, worked on something called aperture synthesis in radio astronomy. If you've ever driven out of Cambridge on the road that heads out towards Biggleswade and Sandy, you've probably seen those fields full of radio telescopes. The Cambridge approach to radio astronomy, started by Ryle, was to have lots of small telescopes spaced out in a regular grid and then computationally join their data together, which simulates having a huge radio dish, if you like. And at the time that was being done, in the early 1950s, the size of dish that people could build was really quite small. In fact, in the UK, it was Dodrell Bank at Manchester, which is a recycled piece of German radar kit, actually. And then one of the Huxleys, I forget which, I think it was Andrew, was also doing work on modeling how information flows in the human nervous system. So it's a very significant scientific breakthroughs were enabled. And each of those Nobel Prize winners, in their acceptance speech, acknowledge EDSAC as if it was another scientist in the team. It's really rather nice. So this EDSAC is mentioned as a player. The first book on programming was written about the EDSAC, written by Wilkes, his student David Wheeler and Stanley Gill, called The Preparation of Programs for an Electronic Digital Computer. And it basically, after a little bit of introduction, waffling on about what computers are, dives straight into here's how you program and operate the EDSAC. And like many people who write books on programming, for the source of examples, it includes listings of the initial orders, which Simon's already called giving the game away, was essentially an assembler, i.e. the compiler, and the library subroutines. And that's kind of become the house style for programming books. You get something general, then you get specifics of the language, and then people give you a listing of the compiler and its libraries, and after that you're supposed to be a programmer. The other aspect of EDSAC, which in terms of the wider use of computing is very significant, is the world's first business computer was called Leo. It was built by a company called Lions, who were a catering company, and they wanted to use computers to do things like inventory control, order management, and so forth. And they literally built a copy of EDSAC. In fact, the story is really rather amusing. They'd heard about computers. They had a discussion at head office and said, we want a computer. We better go to America. And they went and spoke to various Americans who said, you better go back home and speak to this guy Wilkes in Cambridge. He's further ahead than us. They put some money into the project. They assigned an engineer to work on EDSAC. And as EDSAC got working, they essentially copied everything, made a few refinements for what they wanted, and produced the Leo machine very early on. And that's very fortunate because their record keeping is much better than Cambridge's record keeping. And so Leo is much better documented. And though it's not EDSAC, we can read the Leo documents, and where they say, we fixed the blah, blah, blah problem with the XYZ, we now know when we're designing EDSAC, we have to put a blah, blah, blah problem in the XYZ, and then we'll have an EDSAC rather than a Leo. So this definition thing is a little tricky. What actually counts as the first computer? So I've pulled out a couple of examples just to kind of illustrate some of the points. To many people, the first mechanical automatic computer is Babbage's difference engine. Babbage was alive in the 1800s. He designed his difference engine. He never actually succeeded in building it. He had trouble getting it made. He had trouble with fundraising. However, Nathan Myhrvold, who's known to some of us, he was involved in the early days of Microsoft research, funded one to be built, and the Science Museum built two, one for themselves, one for him. So you can go to the Science Museum and see it, or you can go to the Computer History Museum in San Jose and see it. And there's a working difference engine made to Babbage's drawings, and it basically worked. You cranked it by hand, but all the operator was doing was putting energy into the system. It printed out tables, and the calculation of the tables, once the thing was programmed, was all done automatically. So that's arguably an automatic computer, because the operator isn't putting any intelligence, as it were, into the system. Sounds like some modern programmers. In the late 1930s, there was a lot of work on electro-mechanical computers, one at Harvard University. As Tora reminded me, because he made the introduction, in Germany, Konrad Zuse was building electromechanical machines using relays. The problem with electromechanical machines is they really were quite slow by driving relays clicking backwards and forwards, and very, very large. The components were quite big, and so they had their limitations. And indeed, some of the wartime code-breaking machines at Bletchley Park, the bombs that were used to break the Enigma codes, are essentially of that kind, electromechanical machinery. Lots of rotating parts and a large oil sump underneath. In terms of electronics computers, and here's where you start getting even more sort of picky with the definitions, we claim the first digital machine was the Colossus machines at Bletchley Park. These were used for essentially analyzing teleprinter messages that the Germans were sending by radio network to extract the key. The machine didn't break the code. It essentially did statistical analysis, so machine learning, on the messages to look for patterns that were suggestive of what the keys might be. And that, combined with other intelligence, could be used to break the key. And once you broke the key, you could decode all the messages from that day. And so what's going on there, rolls of paper tape with the messages on them, and all the various switches and buttons were where you patched in your guesses as to what the keys might be, and also what you thought the structure of the machine was. It's a fascinating story, well worth reading. The chap who essentially, if you like, broke the system, Bill Tutt, never saw the German coding machine, did it all entirely from the messages, and started off from just one message that got transmitted twice with some minor differences. An operator sent it, his mate said, didn't get that, send it again. His mate said, oh, bugger you, and abbreviated a few things. Two messages with small differences is fantastic for starting to get the key information out. From that, he completely reverse engineered the logic of the machine. He never saw the mechanics until after the war. And essentially what Colossus is doing is running lots of parallel coding machines against assumptions about what the keys might be. It was only in the 1980s, late 1980s, when an Intel Pentium processor could do the Colossus computations faster than Colossus itself could do them. But it can only do the key extraction. You can't program it to do other things. So it's not really general purpose. The Americans had a machine called ENIAC in 1944. This was used for doing calculations for ballistics, where artillery shells might fall and so forth. That had to be wired up by patching. So it could do different calculations, but you spent a day wiring it all up and then you ran calculations through it. So it didn't really have a stored program in the sense that we're used to in the memory of the machine. But it certainly was digital electronics and working very quickly. The first proper computer, in the sense that we understand it today, is the Manchester Small-Scale Experimental Machine, also known as BABY. And indeed, you can see a replica of this in the Museum of Science and Industry up in Manchester, a working replica. The BABY was a full-function computer, but essentially it was built as a test bed for a storage technology based on using cathode ray tubes and the persistence of the dots on the screen as a way of storing ones and zeros. And it was used a little bit for calculation, but not very much, and fairly quickly replaced with a later machine and became a service machine. So Baby beats EDSAC to being the first operational digital computer of the kind we require, and that's why that word practical appears in why we think EDSAC is important. And it's nice that there's a Baby up in Manchester you can go and see, the first computer, and then EDSAC is kind of the first practical one. Very similar technologies, both machines built by people with a background in wartime radar. And if you think about radar, radar is about transmitting and receiving pulses, counting them, so you can work out how long the delay is between a signal being bounced back, and then doing calculations based on that to work out the position of objects you're trying to hunt down. So people who'd worked on radar were already sort of moving into the digital age away from the analog world of radio communications. And both the team at Manchester and the team who worked in EDSAC had that radio background. In fact, they knew each other quite well. And indeed, you may have noticed on the front of my talk, I acknowledged someone called Chris Burton. Chris is the chief designer from the electronics point of view. He, in fact, did the Baby replica as his former project. I'm the project manager and mostly chief mechanical engineer, so I lug all the heavy bits around. So let's talk about EDSAC. That's how EDSAC looked in 1949. It sat in a room in a building that had previously been the anatomy school. It weighed about 2.5 tons. It consumed about 11 kilowatts of electricity. That's 11 bars of electric fire. There was one small window in the room, so you can imagine it was a bit hot and sticky in the summer. People claimed the floorboards would ooze rather unpleasant substances. I think that's part of the apocryphal story. All exposed electronics. There's 250-volt high tension running around that, mains all over the place. And all generally a nightmare. So erecting one of those in an environment that has to meet modern health and safety standards as a museum exhibit brings a few challenges. So the machine evolved. By the mid-1950s, it had got a lot bigger and more complex. And so one of our challenges reading through accounts, looking at photographs, is working out when things happen. And in fact, we have now got a fairly good understanding of the history. The user interface was remarkably basic. You read programs in on paper tape, 5-hole tape of the kind that was used in teleprinters for sending telegrams of the time. You can still get 5-hole tape. There are still a few countries that use old-fashioned telegraph systems, so there are still people who make them. So that paper tape, although the box is labeled Primes 1949, which is the name of the program, the paper tape was manufactured this morning in my home. Oh, there you go. Lost it. So you read programs in on paper tape through a paper tape reader. Has this thing got a little light pointer in it? It must have somewhere. Who knows? Well, you can see the box on the left with the paper tape going through. Mechanical paper tape reader. Output came out on a teleprinter. All that stuff was stolen from the post office where they use these things for sending telegrams and so forth. The thing on the right is known as the 3 oscilloscope unit. They connected oscilloscopes to the machine's memory, so you could see the content of each word of memory. When the machine first ran, it had 512 words of memory. Why do you want more of that? It didn't run Windows. I'm sorry to put you off. By the end of its life, it had 1,024, so double upgrade in size. Through those, you could see the contents of memory, and the machine was actually so slow, you could see the lights twinkle and see what's going on. And we'll show you some of that in a little bit. So built by a chap called Wilkes, who was a mathematics graduate of Cambridge, St John's College, did a physics PhD working with Rutherford in the Cavendish lab, mostly working on the reflection of radio waves through the ionosphere, which is why when the war came along, he was rapidly heaved to go and work on radio and radar type technologies, did a lot of work on naval radar, in fact. When he came back after the war, the chemist who had been the head of the mathematical laboratory got a post at Oxford, so Wilkes went straight from being the office boy to being the director, which is pretty good. And he heard of a conference on computing that was being held at Princeton University in 1947. There was a British mathematics professor, Douglas Hartree, who was well connected with what was going on. And Hartree said, you ought to go to this. Wilkes went to it. He arrived late, but got there in time to collect the papers and mug them up. And if you like, one of the key papers presented at that conference was by John van Neumann, draft report on the EDVAC, which was a proposal for building machine that wasn't actually built till many years later, but was the first blueprint for a computer of the kind that we would understand today, with logic units, memory, and so forth. Wilkes was so taken with this, he decided Cambridge ought to have one, so he designed Cambridge's one on the journey back on the, I think it was the Queen Mary, if I remember correctly, from his memoirs. I guess that was a nice thing in those days. You travelled to conferences on boats. You could write a paper in the time it took to find your way back. There's a limit to what you can do in an 8-hour flight back from Silicon Valley. Designing a computer might be a bit of a challenge. And basically what he designed was a simplified but still practical version of the EDVAC. He accepted all the architectural principles and designed it using the British approach to electronics. He assembled a team to build it. He had a chief engineer, Bill Rennick, who did actually most of the detailed design work. Wilkes kind of did the architecture and the project management. Most of the engineers were electrical instrument makers hired in from local companies. There was a company called Pi who made TV sets in Cambridge, and so people came from there. Most of the metal work was made by a company called Morley and Duke. There used to be a radio repair shop in Cambridge. When I first came here as a student, they're kind of fallen away from being a big electronics company to a little shop down Sydney Sussex Street. They're long gone now. I think it's a handbag shop these days. This is a very posed photograph, but it's the team working on it. And importantly, they had a number of young research students, David Wheeler, John Bennett, who contributed greatly to the design of the machine. And so in the usual way, it's the postdocs who do the real work and put the smart ideas into the system.
Do you know how he funded it?
He doesn't, essentially out of departmental funds, Wilkes refused to be drawn on what it would cost because he never kept accounts. You didn't in those days. In those days, if you ran a university outfit, as Wilkes did, at the start of the year, the university gave you a check, which is your budget for the year, and you put it in your personal bank account, and you hired your people personally, and you ran your department, and next year they sent you another one. So all the modern ideas about transparency and central funding and accounts departments and lawyers, all those things that make your life here so easy. Oh, I do not miss legal and finance and all that. He didn't have to worry about that. So essentially, he would never be drawn on what it cost. It's very hard to estimate. He got a lot of his electronics military surplus, and there was a lot sloshing around at the end of the war. But he certainly spent money because he had things fabricated, he had to employ people and so forth, but we don't know. So the EDSAC architecture, a very familiar shape to anyone who uses a modern computer. There's a store. There's a control component which fetches instructions and executes them. There's an arithmetic unit that essentially contains an adder and a shifter and a single accumulator. The basic machine word length, short words are 17 bits, long words are 35 bits. The accumulator was 74 bits. So if you did a multiplication of two long words, it kept all the bits. And the instruction set was carefully arranged. You could use the accumulator to keep running totals of things. So actually, it could work to very high precision. No floating point. It's all fixed point arithmetic. Floating point was done later on with software libraries. So you scaled your problem so you could always work with essentially fixed point fractions and keep as many digits in the fraction as you can. Not something modern programmers know how to do, but those of us who learned our programming in the late 1960s were still being trained in that because there were still lots of fixed point machines around at that time. So the block diagram is very familiar. The most important part of that block diagram from our point of view is the fact that the store is indeed a separate component. Store technology in the 1940s was a nightmare. They didn't have a very good way of storing data. There were three choices. You could use some sort of rotating electromechanical device. That was slow and not very large capacity. Rotating drums was a standard way of doing it. Manchester had a system based on writing to persistent phosphors and then reading it back. That was a little bit flaky, if the truth be told, and scaling it up to large systems was quite difficult. Those were called Williams tubes, after Frank Williams, who invented them. And the other alternative, which is what the radar community used, were long tubes full of mercury that you sent acoustic pulses down. And the speed of sound through mercury is quite slow. So basically, you could stuff a lot of pulses in a 5-foot tube, and you put the stuff in, you'd read it out at the far end, and cycle it back round again, and you can get about 600 bits in a 5-foot tube. And so you could build your memory by having banks of these tubes and recirculating the data through. The frustration with that is it's a serial medium, and if the word you want to read is the one that's just gone into the tube, you've got a long wait till it comes out again. And so though the interface there shows a single line, there's actually quite a lot of complication where the computer decides it wants to read word N, and it has to wait until the store says, yes, word N is emerging, now you can have it. And so the store and the computer are independently clocked. And for the hardware guys, they didn't have phase lock loops in those days. You just had to design your circuit so they kind of would follow each other. If you open up the structure inside, again, it looks where the data can flow. Again, it looks very modern. There's an input bus so that you can gate information coming out of the store into the arithmetic unit. You can take stuff out of the arithmetic unit. You can gate it into the storage units, or you can put it in something called the transfer unit so that you can essentially cycle it back round and use it again. Multiplies, for example, were done by repeated additions. So you keep sending data into the transfer unit rather than storing it for each step. You could take data from the input channel, the paper tape reader. You could send output to the output channel, the teleprinter. So nice and straightforward. The storage, there was these mercury tanks. All the registers inside the machine were also mercury tanks. The accumulator, well, they were called short tanks. And indeed, the current instruction was held in a tank called the order tank, which captured the bits of the current instruction to be obeyed, which they called orders in those days. And the program counter, which they called the sequence control register, or sequence control tank, that was also a mercury tank. So the whole machine operated in a serial manner. When it wanted to add two numbers in the arithmetic unit, it wasn't like a modern parallel adder where you have two words, you go ka-ching and out comes the result. You would do it digit by digit. So you'd cycle the data out of the accumulator through the half adder and then route it either to the transfer unit or the store and add it digit by digit. So if you can imagine, with the arithmetic being done serially and with having to wait for the memory, the machine did a magnificent 600 or so instructions a second. So not very fast compared to our modern machines. The central clock ran at 0.5 megahertz, which is again a bit conservative, but Wilkes' view was at that speed he knew he could make a machine that worked robustly and he wouldn't have trouble with glitches and so forth. So, what does this machine look like for programmers? Essentially, there are two registers in the machine, the accumulator, which is the working register, and the multiply register. Should have called it the multiplicand. Sorry, it is the verbal. There are three registers, the accumulator, the multiplier, the multiplicand. The multiplicand and the multiplier are used to hold two numbers. When you multiply them, the result gets added to the running total in the accumulator. So you put the two numbers you want to multiply into the multiplicand multiplier, do a multiply instruction, result gets added to the accumulator. So a bit like a modern sort of pocket calculator works. The memory physically is 18 bits long, but only 17 bits are used. That's because of timing challenges. So the arithmetic is 17-bit. There are spare bits sculling around, never got used for anything. 1,024 words is the maximum capacity architecturally. The machine got that by the end of its life. You can read consecutive words at even addresses, i.e. 0 to 4, as a long word, and it reads as 35 bits. That's because you can pick up the 17th bit in the second word because the timing all works out. And so you get a bit more precision if you use a long word than if you store the thing yourself as two short words. And this is kind of evil thing that goes on. So the accumulator, 71 bits in total, paper tape input, teleprinter output, and the initial instructions, initial orders, when you push the on button, that essentially is a very simple assembler. The instruction set is very, very simple. Each instruction consisted of a function which was represented by a letter, and in the teleprinter code used to punch the paper tapes, the bit pattern in memory would be the bit pattern corresponding to a letter A on the teleprinter tape. So if you can hold the tape up to the light and read the letters off, which any EDSAC user can do, and I'm almost there now, you can just read a program off the paper tape and recite it. So, and the mnemonics were fairly helpful. A for add the contents of memory location N into the accumulator. S for subtract. H, load the modify the multiply register from store, V, multiply the multiply register times the store location, adding the result into the accumulator. M was the takeaway. It's like M plus, M minus on a pocket calculator. T was the store instruction and usefully cleared the accumulator. So that happened in 2 steps. There's also a version called U, which left the number in the accumulator. C for collating, just mashing bit patterns, hardly ever used. And most of EDSAC's applications were calculations doing numerical stuff. Using computers to do the logical stuff and so forth wasn't really very important in those days. Shift was a tricky instruction to use because rather than using the address as the number of places to shift, it shifted the number of places that matched the first bit that appeared in the instruction looking from the least significant end. So if I wrote R1, that shifted 1 place to the right. If I wrote R2, it shifted 2 places. To go 3 places, it had to be R4. And if you miss the address off, the address is 0, it's actually whatever digit the last digit of R corresponds to, and I think that was a shift right 13, but I can't quite remember. EDSAC programmers just kind of knew this stuff and lived with it. Left shift, 2 jumps, jump if less than 0, jump if greater than or equals 0. Very frustrating not to have an unconditional jump. At any point you were looping, you had to know what the sign was of the quantity in the accumulator. So the whole batch of programming tactics, so you kind of knew what the sign of things were. To help you with that, and no jump if 0, that would be quite useful too. So no thought really of logical operations of 1 being true and 0 being false or whatever. Input from paper tape to memory, output from memory to the teleprinter. Forget the F instruction, it was abandoned. A no-op, which is really quite useful if you're trying to make programs work. Patching an X instruction over something you want to get rid of has exactly the effect you want. It does nothing, just cycles the machine. The Y instruction did rounding, and Z has the wonderful specification, stop the machine and ring the bell, which apparently is a bit of a sort of cowbell with a bong, though there's no recording of it, so there you go. So a very simple order code. The transistor machine that I have at home, called an Elliott 903, actually has slightly fewer instructions than EDSAC. So EDSAC's instruction set to someone like me feels like a very rich, comprehensive set. So how do you program it? You use subroutines provided as a library via something called a Wheeler jump. What you did in a Wheeler jump was you loaded the accumulator with the address you were at, so you had to know where you were in your program, and fortunately all addresses were positive, so you could then follow that by a jump if positive to the address of the subroutine. The subroutine would then do another addition of its own address to the number you passed in, drop that into the last instruction of the subroutine in the memory, and with a little extra bit pattern, so that when you got to the end of the subroutine, provided the accumulator was still 0, you jump back to the instruction after the one you came to. So there wasn't a jump subroutine instruction. You basically constructed the jumps you needed as you went through. People weren't upset about self-modifying programs in those days. Indeed, if you look at early EDSAC programs, there's endless self-modification going on to scrunch things down. Sorry?
They didn't want to do recursion.
There are some recursive programs, but then you have to kind of manage your own stack yourself. Exactly so.
Oh, silly me.
It's you can read Wilkes, Wheeler and Gill online, and there's an online copy of it, and it's actually a good, amusing bedtime read, particularly some of the library routines coded by Wheeler, who was a very devious programmer, could press things down to a tiny, tiny amount of code. So the instructions were written in a textual notation. So A55F stands for the add instruction on memory using memory location 55, and F means load from 55 as a short integer or a short fraction. A D means load a double word. There was nothing in that assembler for writing data. So you had to encode data as instructions. But fortunately, the letter P is 0 in the teleprinter code. And so decimal 10 is P5F, because P is 0, so you can forget about it. 5 is 5 in the address field. And if you remember from the previous slide, the address field starts at the second bit. And F is fixed, which corresponds to 0. So what you've actually done is put 10 in the word in the memory. And again, as an EDSAC programmer, you carried in your head a lot of those in pseudo instructions that corresponded to useful constants. The other option is you could read them in as numbers. Again, because memory was small, some of the larger programs we've encountered actually come as a suite of 3 subprograms. The first one reads the data in and puts it in memory. You then run the second program that does a computation over that data and leaves the results somewhere else in memory. And then the third step prints them out in some pretty layout, because there wasn't enough to store the numbers to work on and 3 large pieces of software. And people did all kinds of cunning things and workarounds like that. There was a number reading routine as part of initial orders that would read numbers in for you while it's reading in your program and then disappear, so you could use its locations as working storage afterwards, for example. Lots of things. A really useful piece of the initial orders was you could write parameterized addresses, which in a modern assembler you call relative addresses. If I wrote G55 theta, there was a theta on the keyboard and several other Greek letters. What that meant is location 55 relative to the start of the current subroutine I'm loading. And there were control combinations at the start of a subroutine. So I could write subroutines whose addressing was relative, and that was the trick to making programming convenient. Because as a user, I'd punch my program, and indeed I could use relative addresses too. I would then join my program tape, all the library tapes, into one big tape, feed it into the machine, and the initial orders would just lay it out in memory sequentially and do all the fixing up for me, because it knew what theta meant, and indeed you could use other letters in fancy ways. There were various control combinations that are equivalent to the kind of directives you find in a modern assembler. So if you type PKT and then some number like 55K, that would say load the next instruction at location 55. And EM, where M is some address, or E55KPF says end of tape, clear the accumulator, jump to M. If you think you're a good machine level programmer, then go and read the EDSAC initial orders and explain how EMKPF works. And I guarantee it will keep you quiet most of the evening, finding your way around Wheeler's code to see how all that works. The initial orders patch themselves as they run. And most of these directives, once you've unpicked them, you realize they're patching certain things so when you fall over them, the right thing happens at the right time. It's wonderfully obscure. This is how it looked to a user. You'd write your programs on a EDSAC programming sheet, handwritten, and you'd write comments in a comments column. There are, in fact, quite strong conventions about how you might write a program and how you might indicate where there are loops and jumps, how you might distinguish data from instructions and so forth, of which this is not a very good example. The chap who wrote it is one Henry Whale, a New Zealand PhD student. This turned up in his archives. And it's a little bit scrappy from that point of view. The coding sheets had numbers down the side, so you could count off which location in your program each instruction appeared. And then you gave it to a typist who typed it on the teleprinter code. And the paper tape there, what you can see is it is just the punchings of the instructions. No spaces, no new lines. It's just a string of letters and numbers. And in fact, the teleprinter code, the letters and the numbers are all overlapped on top of each other. So it's context sensitive. You have to know the first thing is to be interpreted as a letter rather than a digit. So it's all very, very primitive, and you feed that into the machine. So the way it was done, obviously that's a very error-prone program to get from your handwritten program to the tape. You used a perforator like this. This is Lady Operator. She's reading someone's program from the programming sheet and punching it onto a paper tape. She has no visible record of what she's typing. She's just punching tape, so she's touch typing with no screen, anything like that. Then she would punch it again. As she punched it the second time, she put the first tape in this paper tape reader, and the two would clock through together. And if there's a disagreement, the machine would stop. She would have a think, look at the paper tape, decide whether she had typed the second one wrong or typed the first one wrong, flick a switch to decide which way the thing was to be corrected, and that way you get a correct tape. All done completely blind. So again, you had to have this skill of reading the paper tapes. And your program output, this is the output from Whale's program, came out on a teleprinter, and you didn't waste machine time or memory printing out headings or whatever. You just printed out numbers, and indeed you didn't bother with decimal points, you didn't bother scaling things, because you did all that by hand afterwards. That's original output, original paper tape. So how are we building the replica? As I said, we don't have a complete blueprint. We want to be consistent with the photographs and the records. We want to use period components and circuits. If you looked at those cardboard boxes, you spotted they were those valves were put in those boxes in 1943. Some of the boxes we've opened have been wrapped in newspaper, and it's period newspapers, and they make an interesting read as part of it. Where we can't use period components because they're not obtainable, we'll use modern components and camouflage them. Not had to do very much of that. We absolutely are sticking to the EDSAC architectural principles. So we want to be as close to the original as we can. So we have some technical description and diagrams from the computer laboratory. We have original photographs. There are quite a lot of published papers from the early days. We have recollections of the pioneers. So we need to decide which EDSAC we're building. We have a floor plan. This is an area that measures about 15 feet square, so it's physically quite large. 3 rows of racks. We know broadly what each set of racks does, and we've got 2 copies of, oops, sorry, wrong presentation. We have another diagram, another report, which helpfully fills in what the 3 blank sets of racks do in the back row. The things labelled batteries are large wooden coffins, as they were described, containing the mercury tanks for the memory. So the physical design was actually fairly straightforward. There are a couple of surviving EDSAC chassis, these objects, all identical, which is very frustrating. If there are different parts of the machine, that would have given us more data. One in the computer lab, and others in museums. So we took that 2 bits and measured it. In total, we've got 12 racks to fill, and it's actually near 140 chassis, which in those days they called panels. I have this terrible nightmare giving these talks. Do I use the original words, the modern words for these things? So we measured up the original. We used computer-aided design to do that for us. And we've had a local company in Cambridge called Tevra Engineering who've done all the metal bashing for us. One of the interesting things about EDSAC is EDSAC was used to design its successor, EDSAC 2, for doing simulation and calculations and so forth. We're using modern computers to do a lot of design and simulation for EDSAC. And certainly that's making our life much easier than it was the original pioneers who didn't have a computer to help them. They did it all by old-fashioned pencil and paper methods and so forth. When I wrote this slide, we didn't know how many types of chassis there were or where they were in the racks. We're now in a much happier place, and I've got a picture of that. Also, we need to know how the machine works in detail. We've got diagrams from people's notebooks. There's evidence of lots of change in commissioning. There are whole areas for which there's just no information. So we built ourselves a logical simulation of EDSAC using a program called ELSI, EDSAC Logic Simulator. So the kind of logic diagrams we get will be like this. It breaks down the pictures of the machine into some of the individual units, like particular tanks, mercury delay lines, various functional units, like an accumulator and an accumulator shifting unit. Sometimes that maps to individual chassis. Sometimes it maps to 2 or 3 chassis. There's no information about that. But it broadly shows you how the control signals are flowing around the machine. And other diagrams tell you what the timing is. PI on those diagrams is pulse intervals, and that tells you what the delay is permitted between the signal leaving one part of the machine and getting to another. So some of those diagrams are really quite helpful. From that and information about the overall timing of the central clock that drives the serial system, we were able to build ourselves a logic simulation. I think my slides got out of order. And what our logic simulator gives us is these kind of pictures that show us how the machine is clocked, what signals are turning up where, at what time in the machine. This simulator can run programs, so we're fairly confident it's EDSAC. Obviously, it's a simulator on the real machine. Our pulses don't have nice clean edges like that. There are all kinds of delays and echoes and so forth. What we've done in the last month or so is we have arranged that our simulator can emit a description of EDSAC in something called Verilog, which is a hardware description language. And for the kind of FPGA kits that companies like Xilinx provide, they give you translators that read in Verilog and wire up the FGPA to an electronic system that has the same behavior. And so we've been able to program a transistor-based system to run like EDSAC. And that runs at about EDSAC speed, which is really rather nice. So we have a sort of EDSAC in a matchbox. The idea of that, of course, is then we can plug individual bits of EDSAC into that FPGA as a test harness and use it to exercise other parts of the machine. So I said everything in EDSAC is serial. The attraction of that is it reduces the number of components. You've only got to have a 1-bit adder for the accumulator because you're only adding 1 bit at a time. All the storage is in these mercury tanks. So it seems very attractive for reducing the size of the machine that makes it less expensive and also more reliable because there are fewer things to go wrong. But every now and then you do have to go parallel. Like when you want to address memory, you actually need the address and you want to present a number to the store and say, when this location comes round, please match and give me the answer. And so one of the more complex bits of the machine, and we're in the middle of unpicking it at the moment, we have a working prototype just about, is called the coincidence system. It is well named. It's supposed to detect coincidence between what the computer wants and what the memory can offer. And if it does work, it is an amazing coincidence. And essentially, it's doing serial to parallel conversion through decoders. And actually, it turns out to be a big chunk of the machine. About a quarter of the machine is doing that serial to parallel decoding just to access the memory. So not going parallel to arithmetic unit, it's not obvious it was such a big saving. And certainly EDSAC 2, and indeed most other machines after EDSAC, though not all, one that Tony worked on, the 803, was serial. Most other machines went parallel. The saving wasn't really as high as people thought it might be. I've done logic simulation. Electronics, that's where we have very little information. It's all what's known as AC coupled circuits. Any of you who work with modern electronics, you live in the world of DC coupled circuits. 0 is a reference voltage, 1 is a reference voltage. Everything is smoothed out with capacitors. All your pulses are nice and square. If you're working in EDSAC, you're always thinking about waveforms and adding and subtracting waveforms. You have to think more like a radar engineer or a radio TV engineer and how the waveforms behave. Logic is expensive. An AND gate uses 3 of those valves in cans that are flying around the room somewhere. They're probably all in Brendan's pocket by now. There you are. And 3 diodes, little smaller valves, which is about 1/3 of a chassis for one gate. So you try and avoid using logic, where you can do things by using amplifiers and just straightforward circuits using resistors and capacitors and so forth. You do. So the world you live in is one where transistors are free and they're more than you know what to do with. This is a world where resistors and capacitors are free and transistors are very, very expensive because they're called valves. The components, however, are very familiar to a modern hardware designer: flip-flops, inverters, pulse amplifiers, and so forth. Typical circuit diagram we get. There's an obvious problem with this circuit diagram. There are no component values on it. It's called a flip-flop. We expect a flip-flop to be something you pulse to hold a 1 or you pulse to hold a 0. It turns out in a serial machine, all you need are monostables. They hold a value for a period, as long as they're needed before, as it were, the circuit has moved on. And this is actually a settable monostable, and that's what flip-flop meant in 1949. So how do we map the logic to circuits to chassis? Well, we can try and use the photographs, and indeed, if you start blowing up some of the photographs, there are helpful labels that appear on some of the chassis. So you get very excited, and you keep blowing them up until you get to about there, and then you're at the grain size of the film that was actually glass plates. You're at the grain size of the silver nitrate. Something you can read, but not all. I can see that says coincidence unit 03/1, but that's because I sort of knew that's what it's supposed to say. Anyway, where are we with the machine? These next 3 pictures show the racks. Anything in green we've built. Anything in yellow we know how to build and someone's working on it. Anything in red we've got someone designing but we haven't built it yet. Anything in white we know what it is but we haven't even started to think about it. So as you can see from these pictures, we're making actually quite good progress. Big chunk of the machine designed. Those are what the memory looked like. We're not going to use mercury delay lines. Obviously, it's risky and costly. It's about £160,000 worth of mercury. which is a challenge. The health and safety things aren't really a major issue. They're only an issue when you're building them, because then they're sealed units, so you don't worry about that. The precision engineering of those tubes is quite demanding. So what we're going to use is a later technology called nickel delay lines, essentially the same physical principles, but using stretch wires. And in the short term, we're using semiconductors to do that. So that's what an original EDSAC rack looked like. These are the modern reconstructions, and I bought one here you can come and look at. I've got a team of about 20 volunteers building them for us. We can still get the valve holders, we can still get the valves. The biggest limitation is modern resistors and capacitors are far smaller than period ones. You can get period ones, but they tend to have drifted off value, and we want our machine to run for at least 20 years before someone has to rebuild our replica. And so we took the decision to use modern components. What we do is buy high wattage ones because they are bigger and fatter, so they're about half the size of the period ones, and they look reasonably okay. So most of the parts we can get. The chassis made by a commercial firm here in Cambridge. Their workshop's got some slightly more substantial equipment in it than mine. Mine is certainly gaining bits and pieces. So there's me and one of our racks in my workshop. Lots of things have to be handmade. There are all kinds of coils and so forth, and along the back of the machine, there were no plugs and socket technologies for interfacing things in those days. You used strips of Paxoline with little metal tags on them and soldered everything together. Those are all lovingly handmade by me in my workshop. Built a machine to do that. So we think it's going to cost us about £250,000 to do, and we've raised 3/4 of that funding, so we're in quite good shape, actually. The first racks will be erected at the museum in spring next year, and we're fairly confident of having a working machine by about the end of 2015. If you want to find out any more about the project, there's a website, www.edsac.org, and there's lots of videos on there of us making bits and pieces. There's a video that dates back to the 1950s of how to program and use EDSAC, nice period piece. You can download an EDSAC simulator, it's worth playing with. You can read Wilkes, Wheeler, and Gill off the network. If you want to build anything, you can come and play. And if I do one more thing, I'll finish up and take questions, and we'll go and drink some wine afterwards. I'm going boggle-eyed. If I go into Windows, which I'm told is an operating system, here's a bit of EDSAC. This is the EDSAC simulator. What you have on the left is an EDSAC program, in that just a sequence of characters and notation. This is a program that prints out a table of primes. What you have on here is an image of one of the oscilloscope tubes, and the buttons on the front of the machine. The user interface was very straightforward. You could clear the memory. In the first days, you did that by a wet finger on the chassis and just touch an earth line. They later refined that and put a little push button in. You would push the start button. The machine would read in your paper tape, and you could see the memory filling up. If I go to other tanks, there you go. So that's about the speed at which initial orders are loading the program. And then the program would run. And if I come back to the bottom tank where the variables are, you can see it doing its sum. This is calculating primes, and as you can see, it gets slower and slower because it's doing it by repeated divisions rather than the sieve method. But this was one of the key demonstrations that ran at a conference in November 1949 to demonstrate what was different about a computer than a calculator. Because to calculate primes, the machine has to take decisions, whereas printing out tables of squares and so forth, which was what the first program did, an automatic calculator could do that, but only a computer can do primes. And again, programmers in those days, there was no test to terminate this program. When you got bored with the answers, you push the stop button. If you don't push the stop button, the machine keeps grinding on, and the words you get integer overflow, and all kinds of evil things happen. But you didn't waste memory doing things like checking for the end. You just pushed the stop button when you got the answers you wanted. It was a much simpler age. So I've overrun, but I always do. But I'll happily stop, take a few questions, and then we can probably adjourn outside. Thank you very much.
Thank you very much, Andrew. That was fantastic.
We will just take I think one or two quick questions. I think you were first.
What does the dial do?
Telephone dial. That's a 1951 question. So strictly speaking, I can't answer. What it did was simulate pressing the reset button, which essentially restarts the execution cycle with the digit dial, the last digit dialed on the telephone dial, added to the accumulator. So if you carefully cleared the accumulator and did a stop, the user could type a number in, the program would resume with that number in the accumulator. And so it was used for fairly simple input. It only edited the accumulator, so you had to decide what to do with the data. But there are a number of debugging routines that, for example, would ask you what region of memory you wanted printed out, and you dial the memory location you wanted printed out on that dial. There are various, if you've looked for this simulator at the Warwick site, there are various games like noughts and crosses that use it. There was an EDSAC noughts and crosses game. We've lost the original, but someone's recreated it. There's quite a nice Mandelbrot demonstrator that uses the oscilloscopes, and you dial which quadrant you want to dive in through. And who needs mice and all these things? Paper tape and telephone dial in the world is your oyster.
Yeah, Ken?
I'm curious, when did nickel take over from mercury?
So how sort of close are you to that?
So nickel delay lines were widely used in machines from the early 50s onwards. And essentially, nickel delay line was the first robust memory technology. Core stores came, I guess, late 50s, early 60s, Tony? Early 60s, yeah. I'm a child of the core store age. Certainly, a number of the large commercial machines of the 50s, like the Franti, Pegasus, used nickel delay lines. Very robust technology. Lots of information around about it, but the techniques for manufacturing have been lost. So I have a colleague, Peter Linnington, who used to be a professor of computer science at Kent, now also retired, who literally has gone back to the physics and rediscovered the metallurgy of how you stretch it to get the right properties, how you coil it so it's not a huge long length of wire, how you support the coils, how you suppress the echoes, and so forth. And he's doing a whole little sub-project all of his own, reinventing the manufacture of nickel delay lines. He's built a working short delay line. Long delay line is proving a little bit problematical, but we could always join two short ones together.
I guess the valves, sorry, quick question. The valves were designed, obviously, originally as amplifiers, I guess, and then were sort of hijacked and used as switches. I mean, does that mean that, could the design of the valve have been changed to be more optimized to be a switch?
That's called a transistor.
Well, I mean, for example, can you run them at sort of half power or something until they don't...
no, it's actually worse than that. Because you're using them digitally, you want them operating outside of their linear range, which is where they're good amplifiers. So you're pushing them to either extreme. In the same way that CMOS is a nightmare because it leaks current when it's operating, there's a huge amount of earth leakage. And so designing the power control system for this to meet modern healthy safety standards is quite entertaining. It's going to be a large cupboard full of quite complex electronics.
What was the sort of mean time between failure then? Because the more valves you have, the more...
They got about 35 computing working hours out of the machine a week. The mode was, it was looked after by engineers during office hours who kept it going. After hours, privileged users could use it. If it broke, you walk away, unless you were Joyce Blackler, who became Mrs. Wheeler, in which case David would hang around and fix it for you. Their biggest problem was, because every chassis was different, they couldn't have lots of spares. So if anything broke, you had to take it off and fix it. Another attraction of a parallel machine, like EDSAC 2, particularly if you build it as bit slices, is you have lots of common chassis. And that, again, was a lesson they learned. But the wartime radar experience have proved that quite complex valve electronics were a lot more reliable than people thought. There's another myth that you need to be very gentle with the power on sequence for valves. The experience from Baby in Manchester is people are far too fretful about that. We will sequence our power on, but we're not going to wait 2 hours for the valves to warm up. 30 seconds seems to do it. I literally pulled it out of a rack in my workshop, and it's been running for weeks. This is a digit pulse generator, and it goes blip on the oscilloscope once every 2 milliseconds. Right, it's been doing it for several weeks now, so it seems to be fine. It might sulk when I take it back home because it's been for a trip, but there you go.
Question in the back there?
So you say the subroutine was invented. Were there any other programming advances over the history of EDSAC that were done on EDSAC itself?
No, and the next big advance was index registers, or B registers, and I think Manchester got there first with that. Pretty sure, with their machine. EDSAC did get an index register at the end of its life. No, and once the system, essentially by 1951, the system was just heavily used, built as a service machine. Other innovations, the whole debugging system, but again, that was ready by 51. There's a whole lot of post-mortem software for dumping out memory. There was what we would call profiling these days that printed out an instruction trace as your program executed. And there was numerical trace that printed out the content of the accumulator essentially every time it was stored. And so with those, you could debug programs. There's a very good account by Wilkes. One of his early programs, he kind of wrote to use. He used EDSAC to use tables that he published in various journals of physics and so forth. And an early one was something called the Airy integral. It was a very straightforward integral. And he gives an account of walking away from the machine for the 10th time when his program hasn't run, realizing that programming wasn't as easy as he thought it was going to be. And so it's very clear, it came as a big surprise to them that you don't just write correct programs from the get-go, and you need a lot of support to do that. And debugging at the level of single stepping and watching on the scopes, you could do that, but it was very inefficient, and the queue of users, the way the machine got pretty angry with you. So speeding up that process. And for these profiling systems, they had interpreters, essentially threaded interpretation as part of the way that worked. So some of those kind of ideas were there from the earliest days. They did interpretive floating point later on. And in some of the subroutine stuff, there's some interesting things about parameterization. Own variables were essentially there in modern words. But again, in the assembly code world, these things aren't quite as meaningful as they are in the world of high-level languages. There was never a high-level language for EDSAC. It never had a programming language beyond the simple assembler. Didn't need it.
Thank you. I think in the interest of time, we'll sort of draw the formal proceedings to a close there. I'm sure Andrew will be happy to answer questions over a glass of wine. And hopefully one day you'll come back and give us the other tutorial on restoring old aeroplanes, which I think is what you do in your spare time.
Absolutely.
Meanwhile, let's thank Andrew for a fascinating talk.
I'm designing wings at the moment.